Yes, well, thanks so much for having me, and thanks everyone for coming. Marilyn, I noticed you have a dog dressed up behind your head, and that's also my dog dressed up behind my head. It's kind of funny. Okay, anyway, my name's Carey Hengstenberg. I work at the Department of Environmental Conservation, and I know Sarah because I am the program director for the ECO Americorps program now. But before I was in this role and sort of various administrative things I do now at the agency, I was a geologist, or maybe I still am a geologist. So I have an undergraduate degree in geology where I studied a lot of paleontology and paleogeography. And then I went to graduate school at the University of Vermont and found myself that first summer living in Bakersfield, mapping rocks for the state geologic map. So specifically, the area I worked in that summer was in the Cold Hollow Mountains. But then I wound up doing a lot of my thesis research like in the Northeast Kingdom. But I have studied a lot of Vermont rocks, and hopefully I can share with you some insights today. Sort of hard to prepare for a presentation like this, being so broad and not being in person and having rocks to look at together. Or I think when geologists, often when we teach, we use our hands and like act things out with our bodies. So I'm going to do my best to use my words to describe things, but I did make a PowerPoint with some visuals to hopefully help explain some of what I was going to talk to you about today. And also, one thing I learned in preparing for this, having been away from sort of my technical geologic work for a while, is that geologists make a really lot of complicated maps and documents. So should anyone be confused, like, oh, why didn't I know this? Yeah, I understand why now. I actually was at my office earlier today because there's a bedrock geologic map of the state of Vermont. The original map was made in the 1960s, and they just made a new version of the map in 2012. And the new version of the map is like, it's so big, I can't even show you a picture of it. It takes up an entire wall in a conference room. So I spent some time looking at it because I couldn't figure stuff out, like trying to look at it on the computer. So anyway, if you want further information, it could be a little challenging to find, but I can help you. I'm not used to Zoom, so you're gonna have to bear with me for 2 minutes while I try to share my screen. Okay. Can you see this PowerPoint? Nice.
Yep.
Okay. Before I get into it, I know I just, see, this was part of the problem, was I couldn't get the whole geologic map. Oh, but you could probably see my other screen. I'm just gonna skip ahead. I just start my slideshow. So this is what the current geologic map of Vermont looks like. It is very colorful and it's very complicated. So I'm hoping through this talk we can unravel some of the mystery of what all these colors mean, where these rocks came from, and learn a little bit more. That's all I wanted to show you related to that. Now I'm going back to the beginning. Okay, I also had to look up where the Missisquoi River Basin is. So for anybody on this call that's not intimately familiar, this is sort of the area I was focusing on, learning a little bit more about the geology to share with you. So I wanted to start big picture. I think and again, like, I don't know everybody's learning on geology, so we're just going to kind of like back it up and keep it pretty basic and go more technical as we can. So this is a photo from outer space of the eastern United States. Here you could see little Lake Champlain in Vermont. And then Vermont, I think, as most of us know, we're part of the Appalachian mountain chain, which actually goes all the way from Nova Scotia down, and ends up kind of, the remnants of it are all the way in Texas, actually, of the mountain chain. So this, I just thought, is pretty interesting, how you can really see it, this landform of the mountain ridges. It's another shot, also cool. But Vermont's one little piece of this Appalachian mountain chain. So I thought, for the sake of not boring everyone extremely a lot by showing you a geologic map and reading to you all the different rock units, we might just start by talking about, like, here's a random rock, like, oh, this is a cool rock. You probably see a lot of rocks that look like this when you're out and about hiking in the woods, a lot of them next to highways. So this is a typical rock outcropping. This one is from Waterbury, but it's also from the Hazen's Notch Formation, which is a similar unit of rock that goes up all the way to the Missisquoi watershed. When geologists are mapping rocks and trying to piece together the geologic history of an area, basically what we do is walk around in the woods or on roads or in rivers and water bodies. That's a good place to find rocks exposed. We measure these rocks. We measure, you can see there's like planar features in here, kind of going from the bottom left to top right. We measure how those rocks are placed in the earth. And then we also look at the composition of the rock. And it's basically like putting together a puzzle, because as we all know, Vermont's not like California, where you could just walk outside and see tons of rocks. They're sort of far and few between. So what we do is we walk around, map these different rocks. Back when I was doing it, you know, it was all like on a topographic map with a compass. And then we try to put together the pieces, like we're making a puzzle, we're solving a puzzle. So is this an exact science? No, geology actually is a super creative science, particularly bedrock geology in Vermont, which is probably why that map looks like a beautiful work of art. So this rock, let's say you come across it and you're like, oh, that's a cool rock. I wonder, like, where did that rock come from and how did it get here? This is going to be a long story. All rocks have a really long story. At least all old rocks have a really long story. So we're going to go way, way back to, I'll bring your geologic timescale here. Geologists talk in terms of the geologic timescale, and there's different periods. So at the bottom of the timescale, you see the Proterozoic. I guess nobody really knows a lot about what happened between the Earth, when the Earth was formed 4.6 billion years ago and 540 million years ago. So we largely just call that the Proterozoic, like the time where we don't really understand what happened. And then the Cambrian period started 40-ish million years ago. And we started to go up through time. I think people have probably heard more of the Triassic and Jurassic, because that's when dinosaurs evolved into the Earth. And then more recently, from 666 million years ago, is sort of like more recent times, where we look at a lot of sedimentary features and less rock. So in this area of Vermont that you were all in, these rocks are Cambrian aged. So they're somewhere between 500 and 541 million years old, give or take. We're talking about geologic time, so it's not exact. But something to know about the Cambrian time period is, this is the other reason this is a boundary on the geologic time scale, is because this is when life really started to take off. So prior to this, there were, like life on Earth, people say was first discovered 3.7 billion years ago in blue-green algae, interestingly enough, still around. And, there are some various sea fossils that people have found, but really life on Earth really started proliferating during this Cambrian period. So this is a shot of what the ocean would have looked like during the Cambrian period. And this is important because that is where the sediments that eventually turned into these rocks came from. So things that existed in the ocean were trilobites on the bottom. Some people have probably heard of them. They went extinct at the end of the Cambrian period, but there was lots of them then. That other like squid-like thing in the middle is a nautilus, sort of like a squid. And in the Champlain Islands, you can see some of the fossil remnants of those, along with other things like bryozoans and other simple organisms. So think about this is where we were, in an ocean basin with the animals swimming around. At this time, there was no life on land, no trees, no animals, really just the ocean. Okay, so that's the ocean part. The other part is, while life is going on in the ocean, on the geologic time scale, the plates on the Earth are moving. And so that's something called plate tectonics, which some people probably have heard of, but it really didn't come into being like mainstream to like, or even like accepted by the geologic community to like the 60s or 70s. I can't remember the person who kind of founded the concept, but people thought, that person was really like out in left field. So the concept of plate tectonics, described really simply, is, the Earth is a sphere, and if you had an eggshell that was cracked in a couple different places, and you could move those pieces of eggshell around, that's what's happening at the Earth, like all the time. There's plates that are moving, and they move really slow, but actually some of them move sort of quick. I don't have my facts straight, but there are some places where plates are moving like 1 centimeter a year. And when plates move, that's when, oh, I know what I wanted to show you. Hold on. This is a better visual, but I can't leave my presentation. Google Earth. This will just take a second, maybe, or 50. But when plates move, that's when we have things like earthquakes happen. And seafloor spreading. And if you look at Google Earth, I like looking at it because it's really cool, because you can see the seafloor spreading. promise this is important. You really give you a lot of freedom in Google Earth. All right, here, this is where we wanted to look. So these trenches in the sea are actually places where two plates on the Earth are moving apart from one another. So if you could imagine them going to the right and the left of the screen, and as they're moving apart from each other, there's volcanic activity in the ocean, pushing up through the ocean crust and pushing those plates away from each other. So essentially like creating new Earth in the middle. So the rest of that Earth has to go somewhere because, you know, the Earth is a finite size. And then just bringing into some more concepts real quick to set the stage. Yeah, so when seafloor spreading happens, it pushes the Earth out of the way. And by pushing the Earth out of the way in some places, we call that divergent plate boundaries. Someplace else, you're going to have something called a convergent plate boundary, where two plates collide with each other. And that's when mountains are formed, volcanoes are like land-based volcanoes are formed when that happens. And so, you know, some of the places where there's mountain building that's still going on are like the Himalayas. That's why they're still growing. The Rocky Mountains would be another place where there was a convergent plate margin. They're not still growing from convergent plates. Some mountains grow for other reasons, like the Adirondacks are still growing too. But if you could imagine, this is sort of the setting that we were at in Vermont. Another really important thing to understand when you're trying to piece together geologic history is this whole concept that the present is the key to the past. There was a very famous geologist in the 1600s, wasn't really a geologist, I don't think they had those then, Nicholas Steno, but he was a scientist who kind of first made these pretty, what seem to us now like pretty simple discoveries, but at the time were very different, you know, and one was that like all sediments are originally deposited horizontally. Okay, that makes sense to us now, but back then it was different, and that there's this law of superposition that when you're looking at layers of rock or sediment, the oldest are on the bottom and the youngest are on the top. So those are still like some of the key principles in studying geology today. And yeah, it's very interesting. So Nicholas Steno was what they call him the father of stratigraphy. Stratigraphy is people who really study the details in all of these different sedimentary layers. And he wound up leaving science to join the Roman Catholic Church and never published any of his work. That's just a side tangent. Okay, a few other things. When we have land masses moving apart from each other, so this could have been what was happening in Vermont. That's why I'm showing you this. We had a land mass separating apart from each other, and it makes something called an alluvial fan. So this is not necessarily like a water feature, let's say, but it is formed by water and erosion. And as these rocks rift apart, erosion just continues to happen. And if you think back, like we all remember 540 million years ago, there was nothing on the land to prevent erosion. So erosion was pretty significant. And obviously, as I said before, converging plates make mountains. So that also happened in Vermont a little after 540 million years ago. for 100, no, yeah, about 100 million years later. Whew, right. I'm going to show you some other pictures now. So this is what geologists call paleogeography. There are ways based on looking at rocks, different places, looking at, in particular, minerals that are magnetic and align along the Earth's poles, north and south, which also change over time. If people didn't know that, the Earth's poles spontaneously reverse about once every 100,000 years, and we're due for that. Anyway, point is, in this late Proterozoic period, so this is the time before the Cambrian, there was a supercontinent on the Earth that was called Rodinia. Have people heard of Pangea? Okay. So Rodinia happened like before Pangea, but it doesn't get as much attention because I think it does not involve dinosaurs. So back then, there's this continent called, or this terrain plate called Laurentia. So Laurentia is what is now North America. So this little star that I have in all these maps I'm going to scroll through in the next few minutes, because I couldn't find a good online animation, is how Vermont moved over time. So 650 million years ago, Vermont was like down near the South Pole. During this Cambrian period, so now we're at 514 million years ago, you could see that Vermont is here near the equator, but below the equator. So at the time that these rocks in Vermont originated, the United States was oriented a lot differently, because you see Alaska is up here, so it's like turned 90 degrees, and Vermont was below the equator in what we presume was like a tropical environment, where the type you would find today in that area of the equator. And then over time, it moves. And the big thing that happens here is you see these little ridges like the ones I showed you on Google Earth. That's what's pushing these plates away from each other. And it formed a big ocean basin called the Iapetus Ocean. So all the sediments that made the rocks that we see were deposited in this Iapetus Ocean 514 million years ago or so, plus or minus 50. In an area about 30 degrees below the equator. So then we fast forward a little bit, and you see there's no more spreading going on here. Instead, as these continents are moving closer together, so we sort of switched. Now spreading is happening over here, and it's pushing these continents together. Whoa, and then we get to 400 million years, and you see Vermont's over here, and is just about colliding with this plate called Avalonia. A lot of people in Maine and New Hampshire actually live on what used to be Avalonia. So as Avalonia kind of crashed into the North American continent, Laurentia, the progress of that mountain building event, yeah, so that's what built our Green Mountains and the Appalachian Mountains. That's what I'm trying to say. It happened in more than one phase, which makes the geology a little confusing. Like the two pieces of continental crust that collided together, they had one big collision in like 440 million years ago. That was called the tectonic orogeny. And orogeny in geology terms is a mountain building event. So the tectonic orogeny built the whole western half of Vermont. And then a another second event where this Avalonia terrain crashed into the North America, that was called the Acadian orogeny, and that was about 400 million years ago. Now, though, there was a third orogeny called the Alleghenian orogeny, where some of these other things crashed in, but we don't really see as much evidence of that in Vermont. Anyway, still going. Ooh, okay, yeah. So then, bringing it back to Pangea, here we are during the Jurassic, where the continents are all together. Then they rifted back apart and kind of brought us to this modern day. Africa scooted over this way. We have seafloor spreading, and that's how Vermont wound up where it is. Whew. Brings us back to our rock. Any questions about that? I have like a couple more specific things I could share with you. Might as well share that, and then we can see if you have any questions. So as I mentioned, this is the map of Vermont, and you'll notice if you're not colorblind, and I'm sorry if you are, because this won't be clear, it gives me another reason to, I realize now that these maps are not very accessible, probably by a lot of people. What you see here in the state, and I realize this is not the best, because we can't look at it in high detail.
Put it back on mute.
Okay. But we have this pink color over here, which sort of represents a lot of the rocks that you see in the Champlain Valley and the Champlain Islands, and probably around Swanton, that are gray, mostly gray, shale. You can see some features in them, though. Sometimes you can see like different lines of what we call bedding, where the sediments were deposited. Or you can see places where there's a foliation, where you could tell the rocks have been deformed a little bit by the mountain building event. But largely, like, those rocks have not been changed too much, besides from becoming a rock. As we go east in that brown and green section, these are all the sediments that were deposited in that ancient ocean basin. So there was a big rift. Lots of sediment was deposited into this basin. Over time, this basin closed. And these rocks, which were once sedimentary, are now metamorphic. And how they change to metamorphic rocks is rocks get buried deep in the Earth's crust. You know, so everything we see on the surface, you see there'll be at least as much below the Earth's surface. And when rocks get kind of are under the ground and these processes are happening to them, they're exposed to pretty high pressures and temperatures. So, you know, these rocks in Vermont would have been heated up to somewhere between 400 and 600 degrees Celsius. And that would have been happening anywhere from 5 to 15 kilometers down in the Earth's crust. Yeah. And then over time, as sediments erode, these rocks like rise back up and are at the Earth's surface. So, you know, in theory, like, I had this professor in graduate school who said, yeah, like the Appalachians used to be like 25 kilometers high. I don't know if that's true, but but like that's what the modeling will tell you for like how much rock is still below the Earth, that they could tell from looking at through geophysics. Yeah, So what you're likely to see in here is a rock called schist. Another rock called dolostone. I have some pictures of those types of rocks and we can look at those. And then the last thing you're going to see most likely is in these green areas. This is called a greenstone. And this is pieces of the ocean floor that sort of got during the faulting that happened during this mountain building event, little slices of the ocean floor were brought up. So that's actually called greenstone, and it's a metamorphosed basalt, so a metamorphosed igneous rock, as opposed to the rest, which are a metamorphic sedimentary rock. And then everything over here that's blue-ish was added in the second mountain building event called the Acadian orogeny. So the core of the Green Mountains was formed during this first event, the tectonic orogeny. This came over during the Acadian orogeny, and then kind of during and after that happened, because of those heat that was generated in the Earth's crust, sometimes the crust actually melts, and the melt comes up in the form of a igneous rock. And in this case of Vermont, granite for the most part. This here, just for fun fact, is the asbestos mine, which is probably a whole nother presentation. But let's consider that like a sliver of that oceanic crust that somehow made its way here. So zooming in a little bit on your area, I think I just wanted to talk a little bit about what you see on this map and what it means. One question I think people have when they look at the geologic map is, why are all the rock units kind of going north to south-ish? And the reason for that is that the pressure that came from building the mountains, like if there's any engineers here, it's sort of stress. If you apply stress to something, the weakened plane is going to be perpendicular to where that stress was applied. So that is why it looks like this. And if you went out with a compass like geologists do and you measured some rocks you see on the side of the highway, you'll probably find that they're trending northeast, southwest. Just going to get really geeky for 1 minute. This is called a cross section. So this is geologic map is, we're just looking down as if we could see through all the trees and all the dirt to what the bedrock is underneath. This is if we slice it in half and we look at it sideways. And this line represents the Earth's surface. So everything above that are these ancient mountains that have long since eroded. And what you see here in these little lines, these are all faults. And in Vermont, there are something called thrust faults. And thrust faults are interesting because if I bring you back to that law of superposition, where the oldest rocks are on the bottom, if I were to slice this, like that diagram showed, a thrust fault actually takes the older rocks and moves it on top of the younger rocks, which is another reason why Vermont geology is very complicated, because we know the age of some of these rocks, but then they are out of order. So there is this, this over here, kind of going through Swanton. This goes all the way down through the Champlain Valley. This is the Champlain Thrust Fault. It is a world famous fault. mostly because it has this exposure right in Burlington behind the old Rock Point School. And this is pretty rare in this area to see a fault surface exposed and like really still intact. So in this case, this is a shale on the bottom, like the shale that you would see in the Champlain Islands. And over the top of it is something called a dolostone, which is a slightly metamorphosed limestone, which kind of occurs a little further east in Vermont. So this is a good representation of the thrust fault where older rocks were brought up over younger rocks. And it's also sort of representative of how a lot of those rocks that are pink here are not deformed so much over here, like in the Champlain Islands. Yeah, so geologic maps are complicated, but these rocks are younger, and these rocks are older, and then these rocks are younger again. So that part is a little bit confusing if you really wanted to get into the details. So anyway, here's just some examples of some of the different types of rocks you might see. So shale will be more on the western part of your river basin. And shale is one of the only places, like the only place, at least in Vermont, where we find fossils. We don't find them necessarily in your river basin, but there are places like down near Crown Point and in the Champlain Islands where you can find fossils. And then kind of moving along to schist. I'm guessing you see mostly schist when you're out and about. You know, this is what you see when you're hiking any of the mountains in the Green Mountains. This is what you see when you are in the woods. One interesting tidbit, though, is in your area, there's actually two rock formations. One is called the Hazen's Notch Formation. It's a schist, looks kind of like this. And there's another called the Sweetsburg Formation. And both of these rocks have graphite in them. I don't know if anyone's ever noticed that, if you've been sitting next to a river or sitting somewhere and you've like scratched a rock and like gray powder comes off, like the kind that sticks. Anyway, try this when you're out. Because graphite is carbon, so it's the same thing that diamonds are made out of. It's the same thing that pencil leads are made out of. But what's most significant is that graphite was once life in the sea, which is pretty cool. That was metamorphosed over time, and that carbon turned into graphite in the rocks. This is dolostone. I feel like this is the most boring rock. It's pretty not a lot to say about it. It's hard to break. It's hard to drill through. It doesn't have a lot of interesting geologic features, but it's very sturdy. This is an example of a greenstone, like the type of metamorphosed basalt or oceanic crust rock that you could see little slivers of in Vermont. And I just showed this little picture of talc because when I was up mapping rocks in the Cold Hollow Mountains area, we did come across a few talc deposits. And there are some in like Johnson and mixed in within these rocks. So it's possible, like when you're out and about, that you could run into talc somewhere. More fun facts, Vermont was a huge manufacturer of talc for the Johnson & Johnson company years ago, until there was a lawsuit based on people reporting getting cancer because talc also forms very closely with the types of rocks that contain asbestos, like the type of the asbestos mine. These are like a very similar origin, but they kind of just went through a little bit of a different path. So I think they lost that lawsuit, and Vermont doesn't make talc anymore, but for a long time they were huge. Most of the talc mines were in Ludlow in that area, but I think there was one in Johnson. All right, that's the end of my rock talk. Try not to
Thank
make
you
it
so
too
much,
long.
Carey. We'll give like a couple minutes for any questions. If anyone has some, I can monitor the chat. Thank you so much, Carey. I learned so much. Also, I have a bigger appreciation for Google Earth.
I know, right?
And if anyone wants to talk or ask a question, you can just unmute yourself or type in the chat.
And figure out how to stop.
Hi, Carey. This is Jim Townsend, Cynthia Scott's husband. I was told that the mountains, the Green Mountains, are the second oldest mountains in the world. Is that true?
That's a good question. I think it could be true. Yeah, it definitely could be true.
I was told that the oldest were in South Africa, actually.
Yeah, that would make sense. I mean, the Appalachians, I don't know the exact order, but it's definitely one of the older mountain chains. And people always say, like, you could tell older mountains because they're round and green usually, whereas like compared to the Rocky Mountains, they're not. Obviously, this talk didn't cover anything related to glacial geology and all the other things that could have happened to these rocks.
We do got a question in the chat from Russ. He said, so what's the story about the serpentinite outcrops in Vermont? I'm not sure if I said that right.
Yeah, serpentinite.
Serpentinite, there you go.
Yeah, it sounds cooler that way. Yeah, the serpentinite is those are slivers of the oceanic crust that when this deformation happened were carried up through and exposed at the Earth's surface. And so compositionally they're very, very different from all the metamorphic / sedimentary rocks that are around it. The serpentinite is what you'll see mostly around the asbestos mine in Eden. And that belt of rocks actually goes all the way up through Quebec. And there's another asbestos mine there in a town called Asbestos, Quebec. And, you know, there's different types of asbestos. I know that, so if you find serpentine that on itself is not dangerous, but it's actually a pretty cool mineral, but some of their serpentinite that you find in the asbestos mine, over time, like the rocks kind of degrade, and the primary minerals that were there turn into a different type of mineral. And that's sort of how the asbestos forms. That like during this metamorphism, when these rocks are exposed to really high temperatures and pressures, there's also a lot of like fluids, could be water, but could be other minerals that are lighter and don't bond with other, you know, things that don't bond with other atoms as well, just kind of wind up in this mineralized fluid. And then they deposit within some of the cracks. And so in that case of the asbestos mine, the composition was just right that it formed different mineral called amphibole, but these long fibers. There's two types of asbestos. One is an amphibole-based asbestos, and I totally am blanking on the other type. But a lot of people, or like when I was learning my geology in this region, was that the type of asbestos mined in Vermont and Canada wasn't necessarily as hazardous as, or as like loosely fibrous as a lot of other asbestos mined around the country, for what that's worth.
Awesome. Thank you so much, Carey. I learned so much about rocks. I have a much better appreciation for rocks than I did before this. Parker just asked, what's your favorite mineral?
Good question. I think my favorite, I have a couple, but I really like labradorite. Anybody seen that one?
Mm-hmm.
Yeah, it's a feldspar. And Labrador has some of the oldest rocks in the world, but the way the light reflects off the crystal structure, it looks iridescent.
And we have one more question. We'll wrap it up with Jim McCartney. He says, can you talk about how Vermont's bedrock geology influenced the location/path of present day rivers?
Oh, yeah. Well, we don't have a lot of time, but there's a couple of things that could be at play, but I think one of the things is after all of this deformation of the earth happened, there also was, again, another episode of divergence. So where we didn't have, we're in a passive margin now, right now, by the way. They don't think these plates are moving, so we're safe. But there was some extension happening. So like the Lake Champlain basin, like where Lake Champlain is, that's actually a rift valley from some of the all the pressure of the rocks above going away kind of let these rocks expand, sort of like how an ice cube like will crack when you take it out and let it melt. So that's one way that the landforms are controlled. But a second is that depending on the composition of the rock, some of them are much more resistant to weathering than others. So something like that dolostone will be much more resistant to weathering than a shale. Or in addition, like when I was talking about that Champlain thrust, what am I trying to say? Oh, some places where the rocks have been faulted, like that can create an area of weakness that also could be easily eroded for rivers. But I think a lot more of the details on why the rivers form where exactly is probably related to the glaciers. But I think it's really the inconsistent weathering and some of the other structural things that we can't see.
Awesome. Thank you so much, Carey, for the great presentation.
Okay.
Just a reminder for Lindsay to stop the recording.
Yeah, thank you.
And for anyone that wants to watch any of our other recordings, just remind you it's all on our website. We have a great comment, and your enthusiasm for geology is infectious, and you communicate your excitement in such a fun way. And I can definitely,
thank you.
I definitely agree with that, Carey. It was a great presentation. Your humor is contagious. And I want to also invite anyone that's staying on the call. If you want to stay and learn what UMatter is about, we'll be transitioning into our business meeting. And otherwise, I want to thank everyone for coming and to look out for any of our future events. Our next one is in June for a paddle.